Take a single atomic nucleus. It is sitting there, bound together, stable. Now imagine sliding one more neutron into it. Nothing dramatic happens. The nucleus absorbs it, adjusts slightly, and holds. So you add another. Still holds. Then another. And for a while, this keeps working. The nucleus keeps accepting them, keeps finding a way to stay together. But at some point, it stops working. The nucleus starts rejecting them. Then it starts falling apart on its own. Then you are no longer dealing with a nucleus at all. Then you are dealing with something that does not have a name in ordinary chemistry, because ordinary chemistry never had to think about what matter becomes when you push it this far. That is the actual question here. Each neutron you add is a test of whether the structure holding matter together can absorb one more unit of something that neither carries charge nor carries a bond. And the answer changes progressively and irreversibly the further you go. To follow that change all the way down, you have to start with what a neutron is actually doing in there in the first place. Because most people carry a picture of the nucleus as a tight cluster of protons and neutrons packed together like a ball of marbles. And that picture is not wrong exactly, but it hides something. It hides the fact that the neutron is not just filling space, it is doing a job. And understanding that job is what makes everything that follows make sense. The nucleus is not stable because particles are crammed together tightly enough. It is stable because specific forces are operating at specific ranges, and the neutron is part of what keeps those forces in balance. Pull one out, and the balance shifts. Add too many, and the balance shifts in a different direction entirely. Either way, the structure responds. What is that job exactly? And why does adding more neutrons eventually make things worse instead of better? If you like exploring questions like these, feel free to leave a like and subscribe. Tell me where you're watching from, and if there is something about the universe you find yourself wondering about, share it with us in the comments. With that said, let's get back to the topic. The answer starts with why neutrons are in there at all, and what they are actually holding together. Here is the problem a nucleus has to solve. Protons carry positive charge, and positive charges repel each other. In a nucleus, you are forcing multiple protons into a space so small that the repulsion between them is not a gentle push. It is a violent, concentrated electrical pressure acting across distances so vanishingly small that no everyday comparison captures them honestly. At that range, with that charge density, the force pushing protons away from each other is immense. By the logic of electromagnetism alone, every nucleus with more than one proton should immediately fly apart. The fact that most of them do not means something is overpowering that repulsion, and not just barely. It is overpowering it completely, continuously, across every stable nucleus that exists. That something is the strong nuclear force. It is attractive, enormously powerful at close range, and it operates between protons and neutrons alike without distinction. Every particle in the nucleus pulls on its immediate neighbors through this force, and when enough of those pulls accumulate across the structure, they overcome the electrical repulsion pushing the protons apart. The nucleus holds. But the strong force carries one property that will matter enormously later. It is extremely short range. It does not reach across the whole nucleus the way electrical repulsion does. Each particle only feels the strong pull from the particles sitting directly beside it. A proton on one side of a large nucleus does not feel the strong force from a proton on the opposite side, but it does still feel the electrical repulsion from it. That asymmetry is easy to miss early on, and it is the detail that eventually causes everything to start unraveling. Now notice what neutrons specifically bring to this arrangement. A neutron contributes to the attractive pull without adding any electrical repulsion back into the system. It pulls on the protons and neutrons around it through the strong force, and because it carries no charge, it pushes back electrically against nothing. Every neutron placed inside a nucleus adds to the cohesion side of the balance without touching the repulsion side at all. Protons cannot do this. Adding a proton always brings both a contribution to binding and a new source of electrical pressure working against that binding. A neutron brings only the binding, with nothing added to the other side. This is why, up to a point, adding neutrons genuinely helps. A nucleus sitting with too few neutrons relative to its protons is carrying a repulsion load that the strong force is straining to manage. Add a neutron, and the attractive side of the balance gains without the repulsive side gaining anything. The structure tightens. The energy holding each particle in place deepens. You can see this written into the lightest stable nuclei directly. Helium-4 carries 2 protons and 2 neutrons. Carbon-12 carries 6 of each. Oxygen-16 carries 8 of each. At these scales, the ratio sits close to 1:1. The forces are well matched, and the structures are deeply stable. So the picture that forms is this. Neutrons are the structural support of the nucleus. They dilute the proton repulsion, reinforce the attractive binding, and keep the whole assembly from blowing itself apart. The more you add, the more support you are laying in. That intuition feels solid, and it follows honestly from everything here. It is also about to meet the first hard limit built into matter itself. The strong nuclear force has a ceiling. Not a ceiling on its strength, but a ceiling on its reach. It operates across distances measured in femtometers, and beyond roughly 1 to 3 femtometers, it simply stops functioning. It does not weaken gradually the way gravity or electrical force does with distance. It cuts off. A particle sitting just slightly too far from its neighbor feels essentially none of it. This matters enormously once a nucleus grows large enough. In a small nucleus, every particle is close enough to every other particle that the strong force connects them all into a tight, unified pull. The structure is compact, the reach of the force covers the whole assembly, and the binding holds cleanly. But as you add more particles, the nucleus expands. It has to. Particles resist being compressed into the same space, so a larger nucleus is also a physically wider one. Once the nucleus is wide enough, a particle on one edge is no longer within strong force range of a particle on the opposite edge. The strong force between them has effectively dropped to zero, but the electrical repulsion between those same 2 protons has not dropped to zero. Electrical force weakens with distance, but it never cuts off entirely. It reaches across the full width of the nucleus regardless of how large that nucleus becomes. This creates a structural shift that builds quietly at first, and then accelerates. In a small nucleus, the strong force dominates everywhere, and the electrical repulsion is a manageable background pressure. In a large nucleus, the strong force only connects nearby neighbors, while the electrical repulsion accumulates globally across every proton pair in the structure. Every new proton added to a large nucleus adds one more repulsive relationship with every other proton already present. The strong force it contributes only reaches its immediate neighbors. The repulsion it contributes reaches everyone. Neutrons respond to this shift in a specific way. Because they add strong force binding without adding electrical repulsion, they become increasingly necessary as the nucleus grows. A large nucleus needs more neutrons relative to its protons than a small nucleus does, simply to keep the repulsion load from overwhelming the binding. This is why heavier elements carry a neutron-to-proton ratio that drifts progressively above 1:1. Lead, for instance, carries roughly 1.5 neutrons for every proton. The nucleus is not being generous with neutrons, it is compensating for a repulsion problem that grows faster than the binding can naturally keep up with. So each neutron added to a heavy nucleus is doing real structural work. It is patching a cohesion problem that the geometry of large nuclei creates automatically. That patch works until the nucleus has so many neutrons that a completely different problem begins to surface, one that has nothing to do with proton repulsion and everything to do with what neutrons themselves are. Neutrons are not interchangeable units that a nucleus absorbs passively. Each one that enters the nucleus has to occupy a specific energy state, and those states are not unlimited. They fill up. This is not a chemical rule or a biological constraint. It is a consequence of quantum mechanics, and it applies to every particle that has the property of being a fermion, which neutrons are. Fermions cannot share a state. Two neutrons cannot sit in the same energy level at the same time. Each one that enters the nucleus has to find an unoccupied level and settle into it. The lowest levels fill first, then the next above that. This progression is not optional. It follows directly from the nature of what neutrons are, and it has a consequence that starts small and grows with every addition. Each successive neutron has to occupy a higher energy state than the one before it. The first neutrons dropped into a nucleus settle into low, comfortable energy levels, where the binding from the strong force holds them in place with significant margin. But as those lower levels fill, incoming neutrons are forced into progressively higher energy states. A neutron sitting in a high energy state is less tightly bound than one sitting in a low state. It takes less energy to remove it from the nucleus. It sits closer to the threshold where it can simply leave. This means that as you keep adding neutrons, the binding energy per neutron does not stay constant. It decreases. Each new neutron is contributing less to the overall stability of the structure than the one before it, not because the strong force is weakening, but because the available low-energy positions are already occupied. The incoming neutron has nowhere comfortable to go and has to settle for a level where the hold on it is measurably weaker. At the same time, the nucleus is also expanding physically as neutrons are added. More particles means a larger structure, and a larger structure means the short-range strong force is being stretched across more volume. The neutrons being added at the outer layers of an increasingly large nucleus are sitting further from the dense core where the binding is strongest. They are interacting with fewer neighbors. The strong force they feel is real, but reduced simply by the geometry of where they end up sitting. These two effects compound each other. Higher energy states and reduced neighbor interactions both push in the same direction. Each additional neutron is more loosely held than the last. The nucleus is not falling apart yet, but the margin between stability and instability is narrowing with every step. The structure is accumulating a tension that it has not yet had to resolve, and the mechanism it uses to resolve that tension is one that rewrites the nucleus from the inside. There is a ratio the nucleus is always trying to maintain. Not a fixed number, but a range, and that range shifts depending on how large the nucleus is. In light nuclei, it sits close to 1 neutron for every proton. In heavier nuclei, it climbs, because as established, larger structures need more neutrons to compensate for the growing repulsion problem that geometry creates. But that climb is not open-ended. The ratio has a ceiling, and the ceiling is not arbitrary. It is enforced by the physics of what happens when neutrons accumulate faster than the structure can absorb them stably. To see why, you have to hold two things in mind simultaneously. The first is what was just established. Each successive neutron occupies a higher energy state, and is held less tightly than the one before it. The second is something that has not yet been introduced, which is that protons face the same quantum filling rule. Protons are also fermions. Their energy levels also fill from the bottom up. And crucially, proton energy levels and neutron energy levels are separate. They do not share states with each other. This separation matters because it means the two populations can fall out of balance with each other energetically. When you keep adding neutrons without adding protons, the neutron energy levels climb, while the proton energy levels stay relatively low and partially empty. You end up with a nucleus where the highest occupied neutron states are sitting at significantly greater energy than the highest occupied proton states. That gap is a form of stored tension. The nucleus is carrying an energy imbalance between its two particle populations, and physical systems under that kind of imbalance do not simply sit still. What the nucleus does with that imbalance is convert a neutron into a proton. This is not a metaphor or a simplification. A neutron inside the nucleus physically transforms, emitting an electron and an antineutrino in the process, and what remains is a proton sitting in a lower energy state than the neutron it came from. The overall energy of the nucleus drops. The imbalance between the two populations reduces. The structure settles into a more even configuration. This process is beta decay, and it is the nucleus's primary tool for correcting a neutron surplus. Beta decay is not a failure of the nucleus. It is a self-correction mechanism, and for a wide range of neutron to proton ratios, it works efficiently. A nucleus that is moderately neutron-rich will undergo beta decay over some characteristic time, shift its ratio back toward balance, and arrive at a stable configuration. Many nuclei along the chart of nuclides do exactly this. They are produced neutron-rich, they decay once or several times, and they land on a stable ratio where the energy levels are balanced well enough that no further conversion is favored. But beta decay has a rate. It does not happen instantaneously, and it cannot be accelerated on demand. If neutrons are being added to a nucleus faster than beta decay can correct for them, the ratio keeps climbing regardless of the correction mechanism being active. And more fundamentally, beta decay can only correct the imbalance if converting a neutron into a proton actually lowers the energy of the system. At some point, the proton energy levels have climbed high enough from previous conversions, and the repulsion from adding more protons has grown large enough that converting another neutron into a proton would cost energy rather than release it. At that point, beta decay stops. The nucleus has reached a configuration where it cannot self-correct any further, not because the mechanism has broken down, but because the energetics no longer favor it. What you are left with is a nucleus carrying more neutrons than any self-correction process can remove, sitting in a configuration where the highest neutron energy states are weakly bound, the structure is physically large, and the margin between holding together and releasing a neutron has narrowed to almost nothing. The nucleus is approaching a boundary that has a specific name and a specific physical meaning, and crossing it changes what the word nucleus can even refer to. To understand what happens when beta decay stops working, you need to understand precisely what it is doing while it still works. Because beta decay is not simply a nucleus shedding excess neutrons, it is a fundamental transformation happening at the level of the particles themselves, and the mechanism driving it reaches down into the internal structure of the neutron in a way that matters for what comes later in this chain. A neutron is not a structureless point, it is made of quarks, specifically 2 down quarks and 1 up quark held together by the strong force at a level deeper than nuclear physics. A proton is also made of quarks, 2 up quarks and 1 down quark. The difference between a neutron and a proton at the most fundamental level is the flavor of one quark. One down quark becomes one up quark, and the neutron becomes a proton. That transformation is mediated by the weak nuclear force, which is the only force capable of changing quark flavor. The weak force reaches in, flips the quark, and in doing so converts the particle identity entirely. When that flip happens inside a nucleus, the energy released by the conversion has to go somewhere. It leaves the nucleus in the form of an electron and an antineutrino, both produced at the moment of transformation. The electron flies out carrying kinetic energy. The antineutrino flies out carrying the remainder. What stays behind is a proton sitting in an energy state lower than the neutron occupied. The nucleus has shed energy, shifted its internal balance, and moved one step toward a configuration where the neutron and proton energy levels are more evenly matched. Now hold that picture and consider what determines whether that conversion is favorable. The neutron in a high energy state has more energy than a proton would have in the corresponding proton level. The system can lower its total energy by making the conversion, so the conversion happens. But the proton levels are not static. Every time a neutron converts into a proton, the proton population grows. Proton energy levels, following the same quantum filling rule, climb as more protons are added. And proton repulsion climbs as well, because each new proton is another source of electrical pressure pushing against every other proton in the nucleus. The energetic reward for converting a neutron shrinks with each conversion because the destination state is getting progressively less favorable. At the same time, consider what is happening on the neutron side. If the nucleus is being loaded with neutrons continuously, the neutron energy levels keep climbing, regardless of how fast beta decay is running. Beta decay is pulling neutrons out of the high energy states by converting them. But if neutrons are arriving faster than conversions are occurring, the high energy states keep filling. The correction mechanism is real and active, but it is losing ground. There is also a subtler constraint operating beneath all of this. Beta decay has a characteristic timescale that varies by nucleus, but is never instantaneous. Some neutron-rich nuclei decay in milliseconds, others take seconds or minutes. The rate is governed by the degree of mismatch between the neutron and proton energy populations, and by the specifics of the weak force interaction facilitating the conversion. You cannot accelerate it beyond what the physics allows. If the neutron loading rate exceeds what decay can correct in the available time, the ratio climbs regardless. What this means structurally is that beta decay defines a moving boundary. On one side of that boundary, a neutron-rich nucleus is unstable but correctable. It will decay, shift its ratio, and eventually arrive somewhere stable. On the other side of that boundary, the nucleus is carrying a neutron surplus that no decay process can bring back into balance, either because the energetics no longer favor conversion, or because the structure itself can no longer be described as a bound nucleus in any conventional sense. That boundary is approached gradually, one neutron at a time, and crossing it does not produce a dramatic visible event. It produces something quieter and more absolute, a nucleus that simply cannot hold the next neutron at all. There is a point in the neutron loading process where the nucleus is no longer correcting towards stability. It is simply failing to fall apart quickly enough to keep up with what is being added. That distinction matters because it changes what the nucleus actually is at that stage. It is not a stable structure absorbing stress. It is a structure in continuous collapse that has not yet finished collapsing. Every neutron added beyond the correctable range is not being integrated into the nucleus. It is being momentarily trapped in a configuration that is already in the process of rejecting it. To see why this happens mechanically, consider what the outermost neutrons in a heavily loaded nucleus are experiencing. They are sitting in high-energy states, as established. They are physically located toward the outer edge of the nucleus, where the density of neighboring particles is lower and the strong force pulling them inward is weaker than it is for particles near the core. The binding holding them in place is marginal. The energy gap between their current state and the threshold for simply leaving the nucleus has become very small. In a stable nucleus, that gap is large and comfortable. In a heavily neutron-loaded nucleus, that gap has been compressed to nearly nothing by the progressive filling of energy levels and the physical expansion of the structure. Now introduce one more neutron. The available energy states it can occupy are not just high, they are at or above the threshold where the strong force binding can no longer guarantee confinement. The incoming neutron settles momentarily into that state, but the binding holding it there is so weak that the slightest perturbation, the natural quantum fluctuations that operate continuously inside any nucleus, is enough to push it back out. The neutron does not stay, it is emitted almost immediately after being absorbed. The nucleus has reached a configuration where it is actively shedding neutrons as fast as they arrive, not through beta decay, not through any conversion process, but through direct neutron emission. The nucleus is exhaling neutrons because it structurally cannot hold them. This behavior has a name. A nucleus that emits neutrons directly without any conversion process is described as sitting beyond the neutron drip line. The name comes from the image of neutrons dripping out of the nucleus the way water drips from a saturated surface. The material cannot absorb any more. What arrives simply runs off. But the image undersells what is actually happening, because a dripping surface is passive. What the nucleus is doing is active. It is a quantum mechanical rejection, happening on timescales so short that the neutron's residence inside the nucleus is barely meaningful as a bound state at all. What makes the drip line a genuine physical boundary rather than a gradual transition is the sharpness of the energy threshold it corresponds to. Below the drip line, a nucleus can be neutron-rich and unstable, but it holds together long enough for its instability to be a property of the nucleus as a defined object. You can measure it, characterize it, describe its decay mode and half-life. Above the drip line, that description breaks down. The neutron separation energy, which is the energy required to remove a neutron from the nucleus, has dropped to 0 or below. A negative separation energy means the nucleus is not holding the neutron at all in any thermodynamic sense. The neutron is not bound. It is passing through a temporary gravitational equivalent well that is too shallow to contain it. Beyond this point, the question of what happens when you keep adding neutrons can no longer be answered in terms of nuclear structure as it is conventionally understood. The nucleus, as a bound collection of protons and neutrons held together by the strong force at femtometer scales, has reached the limit of what that description can contain. The next stage of the answer requires asking what happens when neutrons are not being added to a nucleus at all, but are instead accumulating as bulk matter, in quantities so large that the organizing framework is no longer atomic, but gravitational. The scale shifts entirely, and with it, the forces that determine what structure is even possible. The neutron drip line is not a line in any spatial sense. It is a boundary on a map of nuclear existence, a map where one axis tracks the number of protons in a nucleus, and the other tracks the number of neutrons. Every point on that map represents a possible combination of the two. Some of those combinations correspond to stable nuclei. Some correspond to unstable nuclei that decay but exist long enough to be measured. And some correspond to combinations that simply cannot exist as bound objects at all. The neutron drip line is the boundary between the last two categories on the neutron-rich side. Cross it, and you are no longer in the territory where nuclei exist as meaningful structures. What defines that boundary physically is the neutron separation energy reaching zero. The neutron separation energy is the amount of energy required to remove one neutron from a nucleus cleanly. In a deeply stable nucleus, this value is large. Several million electron volts of energy would need to be supplied to pull a neutron free. In a moderately neutron-rich nucleus, that value has decreased but remains positive. The neutron is still bound, still held inside the structure with a real energetic commitment from the strong force. As more neutrons are added and the energy levels feel higher, that separation energy keeps decreasing with each addition. The neutron at the outermost occupied level is always the most weakly bound, and its separation energy is the one being watched. When that separation energy reaches zero, the outermost neutron is no longer bound in any meaningful energetic sense. It costs nothing to remove it, and when it drops below zero, removing the neutron actually releases energy. The bound state is not just weak, it is thermodynamically unfavorable. The neutron is more stable outside the nucleus than inside it, which means the moment it arrives in that configuration, it leaves. There is no delay driven by a decay process, no conversion that needs to occur first, no half-life in the conventional sense. The timescale for emission is governed by the quantum mechanics of tunneling and resonance, and it is extraordinarily short. The neutron's time inside the nucleus at that point is measured in units so small they have no intuitive meaning in everyday experience. Now consider what this means for the structure of the nucleus itself in this regime. A nucleus sitting just at the drip line, with its outermost neutrons barely bound, develops a feature that has no analogue in stable nuclei. The outermost neutrons, being so weakly held, occupy quantum states that extend spatially far beyond the core of the nucleus. In a stable nucleus, the neutron wave functions are compact and concentrated around the nuclear center. In a dripline nucleus, the wave function of a barely bound neutron stretches outward into a diffuse cloud surrounding the tightly bound core. This extended structure is called a neutron halo, and it has been observed experimentally in nuclei like helium-6 and lithium-11. The nucleus develops a skin of quantum probability that reaches distances several times larger than the core itself. The boundary of the nucleus becomes genuinely ambiguous, because the neutron is simultaneously associated with the nucleus and barely distinguishable from a free particle drifting nearby. This halo structure represents the absolute outer edge of what nuclear binding can produce. It is matter at the threshold of cohesion, held together by the weakest possible expression of the strong force, with quantum mechanics stretching the geometry of the nucleus into something that looks almost nothing like the compact sphere that the word nucleus typically suggests. The dripline nuclei that have been studied experimentally are produced in accelerator facilities under carefully controlled conditions, lasting long enough to be detected before their outermost neutrons depart. They are not found in nature under ordinary conditions because the conditions required to produce them do not exist in stable environments on Earth. But they do exist elsewhere, in the crusts of neutron stars, where pressures and densities reach levels that no terrestrial laboratory can replicate. Nuclei are pushed toward and beyond the drip line by the weight of the matter above them. the neutron drip line, which in a laboratory context represents the farthest edge of achievable nuclear structure, becomes in that context just one stage in a descent that continues far deeper. Beyond the drip line, under sufficient pressure, the organizing principle shifts away from nuclear structure entirely. Individual nuclei stop being the relevant framework. What replaces them is something that requires a completely different set of tools to describe, and a completely different understanding of what matter even means under those conditions. Outside a nucleus, a neutron does not survive. This is not a conditional statement that depends on environment or temperature or pressure. It is a property of the free neutron itself. A neutron removed from a nucleus and left in open space will decay into a proton, an electron, and an antineutrino in roughly 15 minutes on average. That 15-minute window is not a half-life in the usual sense of a statistical spread across a population. It is the mean lifetime of the particle itself, and it applies universally to any neutron not held inside a nucleus by the strong force. The reason connects directly to what was established about beta decay earlier. Inside a nucleus, a neutron occupies an energy state, and whether it converts into a proton depends on whether that conversion would lower the total energy of the system. In many configurations it would not, so the neutron remains a neutron indefinitely. The nucleus stabilizes it by making the conversion energetically unfavorable, but a free neutron has no nucleus around it setting those energetic conditions. The conversion of a free neutron into a proton is always energetically favorable, because a proton has slightly less mass than a neutron, and that mass difference is released as kinetic energy carried away by the electron and antineutrino. There is nothing to suppress the decay. It proceeds on its own timeline, driven by the weak force, and it always completes. This creates a constraint that becomes critical when thinking about what happens beyond the neutron drip line. At the drip line, neutrons are being emitted from nuclei because the binding can no longer hold them. Those emitted neutrons are now free, and free neutrons decay. The question of what you get when you keep accumulating neutrons, therefore, cannot be answered by simply imagining a growing pile of free neutrons sitting together, because that pile is not stable on any timescale relevant to structure formation. The neutrons are converting into protons faster than any coherent neutron-rich structure can assemble itself from them under ordinary conditions. The only way to accumulate neutrons in bulk beyond what individual nuclei can hold is to do so under conditions where the decay of free neutrons is itself suppressed. And that suppression requires a specific physical condition that does not exist in laboratories or in any ordinary astrophysical environment except one. The decay of a neutron into a proton produces a proton, and adding protons to a system raises the proton energy levels through the same quantum filling logic already established. If the proton energy levels in the surrounding environment are already filled up to the energy that the decay would produce, the decay cannot proceed. There is nowhere for the new proton to go. The Pauli exclusion principle, the same rule that governs energy level filling in nuclei, blocks the conversion entirely. This condition is called neutron decay suppression through Pauli blocking, and it requires an environment so dense that the proton states available at the relevant energy are already fully occupied. That density is not achievable in any nucleus. It is not achievable in any material that exists on a planetary surface. It requires the gravitational compression of a stellar remnant, specifically the kind of remnant produced when a massive star exhausts its nuclear fuel and its core collapses under its own weight in a matter of seconds. In that environment, the densities reached are high enough that free neutron decay is suppressed. Neutrons accumulate in bulk, And the question of what happens when you keep adding neutrons transitions from a question about nuclear physics into a question about the behavior of dense matter at scales where gravity is the dominant organizing force. The descent has shifted. Individual nuclei are no longer the relevant structure. What comes next is matter organized, not by the strong force binding particles into compact nuclear objects, but by quantum mechanical pressure resisting gravitational compression across an object the size of a city. When the density of matter climbs past the point where individual nuclei can maintain their identities, something structural happens that has no analogy in ordinary material science. The nuclei do not simply compress into each other. They dissolve. The boundary that defines where one nucleus ends and empty space begins stops being meaningful, because the neutrons that were contained within individual nuclear structures are now so densely packed that the concept of belonging to a particular nucleus loses its referent. The neutrons are everywhere, continuous, overlapping in their quantum states across distances far larger than any individual nucleus. What was a collection of discrete nuclear objects becomes a single continuous fluid of neutrons, and the physics governing that fluid is entirely different from the physics governing bound nuclei. This transition happens in layers inside a collapsing stellar core, and the layers reflect the progressive breakdown of nuclear structure under increasing pressure. In the outer crust of what will become a neutron star, ordinary nuclei still exist, arranged in a crystalline lattice held in place by the electrons threading between them. The structure resembles a metal in some formal ways, with nuclei at fixed positions and a sea of electrons providing conductivity. But as depth increases and pressure climbs, the nuclei become progressively more neutron-rich, pushed toward and then past the drip line by the weight above them. Free neutrons begin to appear between the nuclei, filling the space that was previously empty. The crust develops a mixed character, part discrete nuclear structure, part free neutron fluid. Deeper still, the pressure increases to the point where the distinction between inside a nucleus and outside a nucleus collapses entirely. The nuclear structures deform, elongate, and merge into continuous shapes that have been given names reflecting their geometry: sheets, tubes, and interconnected sponge-like configurations that physicists refer to collectively as nuclear pasta. These are not metaphors. They are actual geometric phases of dense matter, predicted by calculations and consistent with observations of neutron star properties, in which the strong force is still operating, but is no longer organizing matter into the compact spherical objects that the word nucleus implies. The matter is in a state that has no terrestrial equivalent, somewhere between a collection of nuclei and a uniform fluid, and its properties depend sensitively on the exact density and the balance between the strong force, the electrical repulsion of the protons still present, and the quantum mechanical pressure of the densely packed particles. Past the nuclear pasta region, the transition completes. The matter becomes a uniform fluid composed overwhelmingly of neutrons, with a small fraction of protons and electrons maintained by the equilibrium between neutron decay and its reverse process. This is the bulk interior of a neutron star, and the neutrons filling it are not bound to each other in the way particles are bound inside a nucleus. There is no strong force bond between one neutron and the next, in the way there is between neighbors in a nucleus. What is holding the entire structure together, and what is preventing it from collapsing further, is something that has not yet entered this chain. It is a pressure that arises not from any force between particles, but from a quantum mechanical rule about what fermions are allowed to do when they are compressed into the same space. That pressure has a name and a precise physical origin, and it is the only thing standing between a neutron star and complete gravitational collapse. It operates without any interaction between particles, without any repulsive force in the conventional sense, and it has an upper limit that gravity can eventually overcome. Understanding what it is and where that limit lies is what the next stage of this chain requires. Squeeze any collection of fermions into a small enough space, and something happens that has no classical equivalent. The particles do not simply compress closer together the way gas molecules do under pressure. They resist, they push back, and they do this not because of any force acting between them, not because of electrical repulsion or strong force interaction, but because of a rule so fundamental to the nature of matter that it operates regardless of temperature, regardless of what the particles are made of, and regardless of how much energy the system contains. That rule is the Pauli exclusion principle, and in the interior of a neutron star, it becomes the primary structural force holding the entire object together. The principle states that no two identical fermions can occupy the same quantum state simultaneously. In a nucleus, this rule governs the filling of energy levels, as established earlier in this chain, but in a nucleus the number of particles is in the hundreds at most, and the space they occupy, while small, allows enough distinct quantum states to accommodate them without extreme crowding. In a neutron star, you are compressing roughly 1 to 2 solar masses of matter into a sphere perhaps 12 kilometers across. The number of neutrons involved is on the order of 10 to the power of 57. The space available per neutron is almost incomprehensibly small, and every neutron needs its own quantum state. When fermions are forced into a small volume, the quantum states available to them have a minimum energy set by the size of the confinement. Smaller volume means higher minimum energy for the lowest available states, which means the particles are forced into higher and higher energy states simply by virtue of being confined. This is not thermal energy. It does not depend on temperature. A neutron star could theoretically be cooled to absolute zero, and this pressure would remain completely unchanged, because it does not arise from particle motion in the thermal sense. It arises from the geometric fact that confining fermions into a small space forces their quantum states to carry energy, and particles carrying energy exert pressure on whatever is confining them. This is neutron degeneracy pressure, and in the interior of a neutron star, it is enormous. The neutrons are packed so densely that the energy of even the lowest available quantum states is extraordinarily high by any ordinary standard. The pressure they exert outward against gravitational compression is what gives the neutron star its structural integrity. Remove the neutrons and replace them with bosons, particles not subject to the exclusion principle, and the same gravitational compression would proceed without resistance. The star would collapse. It is specifically the fermionic nature of neutrons, the fact that they cannot share states and are therefore forced into high energy configurations when confined, that generates the outward pressure holding the object at a stable radius. The neutron star sits in a balance between two competing quantities. Gravity is pulling every part of the star toward the center, with a force proportional to the mass above it at every depth. Neutron degeneracy pressure is pushing outward at every point, generated by the quantum mechanical resistance of the neutrons to further confinement. For a neutron star below a certain mass, these two quantities reach an equilibrium. The radius stabilizes, the object holds. But degeneracy pressure, unlike thermal pressure, does not increase without bound as you add more mass. Adding mass to a neutron star increases the gravitational compression, which forces the neutrons into even smaller volume, which increases the degeneracy pressure in response. Up to a point, this feedback keeps the star stable, but the neutrons are being compressed toward velocities approaching the speed of light, and once particle velocities enter that relativistic regime, the relationship between confinement and pressure changes. The pressure response to additional compression becomes less steep than it would be in the non-relativistic case. Gravity gains ground, the balance becomes harder to maintain, and the margin between stability and collapse narrows in a way that cannot be recovered simply by having more neutrons present. The very thing providing the pressure is approaching a physical speed limit that weakens its effectiveness precisely when the gravitational load is highest. There is a maximum mass beyond which no configuration of neutron degeneracy pressure can hold the star together. That limit is not an engineering constraint or a practical limitation. It is written into the mathematics of general relativity and quantum mechanics simultaneously, and crossing it initiates a process that the neutrons themselves cannot stop. There is a mass threshold above which neutron degeneracy pressure loses the contest with gravity permanently. It is called the Tolman-Oppenheimer-Volkoff limit, and it sits somewhere between 2 and 3 solar masses for a neutron star, with the precise value depending on how matter behaves at the extreme densities involved. Below that limit, the star holds. Above it, no configuration of neutron pressure can arrest the collapse, and the descent into something else begins. What makes this limit physically meaningful rather than just a number is the mechanism behind it. As established, degeneracy pressure in the relativistic regime responds less effectively to increasing compression than it does at lower densities. Each increment of added mass compresses the star further, forcing neutrons into smaller volume and higher energy states. But the pressure response to that compression grows more slowly than the gravitational load driving it. The gap between what gravity demands and what degeneracy pressure can supply widens with each increment of added mass. At the limit, that gap becomes permanent. Gravity is pulling inward faster than any quantum mechanical resistance can push back, and the collapse proceeds. The initial stage of that collapse drives densities past what neutron degeneracy pressure governs, and into a regime where the neutrons themselves are no longer the relevant structural unit. Neutrons are composite objects. They are made of quarks, and at densities high enough, the boundaries between individual neutrons begin to dissolve in a way that mirrors what happened earlier to individual nuclei. Just as nuclei lost their discrete identities when compressed into neutron matter, neutrons lose their discrete identities when compressed past a certain density threshold. The quarks that were confined within individual neutrons begin to overlap with quarks from neighboring neutrons. The distinction between one neutron and the next becomes geometrically ambiguous at the scale of the quarks themselves. What this transition produces, if it occurs, is a phase of matter called quark matter, in which the relevant fluid is not neutrons but free quarks moving through a shared volume. This phase is theoretically predicted, but not yet confirmed observationally with certainty. What is known is that if quark matter forms inside a collapsing stellar remnant, it has its own equation of state, its own relationship between pressure and density, and potentially its own resistance to further compression through quark degeneracy pressure. Whether that resistance is sufficient to halt the collapse depends on the specifics of how quarks interact at those densities, which remains one of the genuinely unresolved problems in theoretical physics. What can be said with confidence is that the collapse initiated when the Tolman-Oppenheimer-Volkoff limit is crossed does not find an easy stopping point. The matter is in a regime where successive layers of structure are being stripped away, where each framework that provided resistance at a previous density scale is being overwhelmed, and where the question of whether any new framework can provide sufficient resistance at the next scale is open. The descent is not guaranteed to stop at quark matter. It may continue through it entirely. To get a concrete sense of what matter is experiencing at neutron star densities, consider what compression at this scale actually means. A sugar cube filled with matter at neutron star core density would contain roughly the same mass as all of humanity combined, packed into a volume you could hold between two fingers. That comparison is not decoration, it is the actual ratio, and sitting with it clarifies why the physics operating in that environment has no terrestrial analogy, and why intuitions built from everyday experience fail completely here. At those densities, the emptiness that defines ordinary matter has ceased to exist. Atoms are overwhelmingly empty space, with a tiny nucleus at the center and electrons occupying states at distances vastly larger than the nucleus itself. At neutron star densities, that emptiness has been completely eliminated. Electrons have been forced by pressure to combine with protons through inverse beta decay, running the decay process in reverse, converting protons and electrons into neutrons and neutrinos. Atomic structure is gone. Nuclear structure is gone. What remains is a continuous neutron fluid packed at nuclear densities, sustained across an object 12 kilometers wide. At that density, the neutrons are touching in the sense that their quantum wave functions overlap completely and continuously. The interior of the star behaves less like a collection of particles and more like a single coherent quantum object of stellar mass, with properties depending on the collective behavior of the entire neutron population. Theoretical models predict that at certain depths, neutrons form Cooper pairs through a mechanism analogous to superconductivity, creating a neutron superfluid flowing without viscosity through the inner layers. The star is not simply dense, it is dense in a way that generates entirely new organizational phases of matter that exist nowhere else in the observable universe. The pressure at the core exceeds the pressure at the center of the Sun by many orders of magnitude, and exceeds anything achievable in any laboratory by a margin so large that terrestrial high-pressure physics cannot approach this regime even remotely. The matter at that core is being compressed by the gravitational weight of an entire stellar remnant, bearing down from every direction, and the only thing preventing further compression is the quantum mechanical resistance of particles already moving at substantial fractions of the speed of light. This is the environment where the final stages of the chain play out. The question that began with a single nucleus accepting one more neutron has descended into a regime where the relevant object is not a nucleus, not a collection of atoms, not a conventional fluid, but a quantum mechanical structure of stellar proportions operating at the boundary of what known physics can describe with confidence. At sufficient density, neutrons stop being the bottom of the structural hierarchy. This is not obvious from everything established so far, because neutrons have been treated throughout this chain as fundamental units, the particles that fill energy levels, resist compression, and form the bulk fluid of a neutron star. But neutrons are not fundamental. They are composite objects, each one containing 3 quarks bound together by the strong force at a level deeper than nuclear physics. And at densities beyond what neutron degeneracy pressure can maintain, the boundaries of individual neutrons dissolve. The mechanism mirrors what happened earlier at 2 previous scales. Individual nuclei lost their discrete boundaries when compressed into neutron matter. Now, neutrons lose their discrete boundaries when compressed past the point where the space between them effectively vanishes. The quarks that were confined within individual neutrons begin overlapping with quarks from neighboring neutrons. At that point, the question of which quark belongs to which neutron has no geometric answer. The neutrons have merged into a continuous quark fluid, and the physics governing that fluid is quantum chromodynamics, operating in a regime that no experiment has directly accessed. This phase of matter, called quark matter, carries its own resistance to compression through quark degeneracy pressure, operating on the same Pauli exclusion logic that governed neutron degeneracy pressure at the previous scale. Whether that resistance is sufficient to halt the collapse depends on the equation of state of quark matter at these densities, which remains genuinely uncertain. The calculations are extraordinarily difficult because the strong force which binds quarks behaves in ways that resist straightforward mathematical treatment at the densities involved. What is understood is that if quark matter forms and its pressure is sufficient, a stable object called a quark star may result. If the pressure is insufficient, the collapse continues without interruption through the quark matter phase and beyond. Either way, the descent has moved past every organizational framework that matter uses under any conditions found elsewhere in the universe. Each layer of structure that provided resistance has been overwhelmed in sequence, from nuclear binding to neutron degeneracy to quark confinement, and the next threshold is one from which no recovery is possible. Past the quark matter threshold, if no sufficient pressure exists to halt it, the collapse does not slow. There is no deeper structural layer to engage, no smaller constituent of quarks that reorganizes into a new phase and pushes back. The descent becomes unconditional. The matter is not transitioning into something denser. It is losing the property of being matter in any structured sense at all. What forms is a black hole, not an object in the way a neutron star is an object, with an interior that can be described in terms of particle phases and pressure gradients and density profiles. A black hole is a region of space-time where gravity has overcome every possible resistance, and curvature has become so extreme that the escape velocity exceeds the speed of light. Nothing that crosses the event horizon returns, not particles, not radiation, not information about what fell in. The chain that began with a neutron settling into a nuclear energy level ends here, at a boundary where the concept of internal structure has no meaning. What this entire descent reveals is that matter has a hierarchy of resistance. Each layer of structure, nuclear binding, beta decay equilibrium, the neutron drip line, neutron degeneracy pressure, quark confinement, holds against compression up to a specific threshold and then yields to the next. Adding neutrons is the pressure that drives the descent through each of these layers in sequence. Every threshold crossed is a stripping away of one more organizational framework that matter uses to maintain form. The neutron you started with, sitting inside an ordinary nucleus, was already part of that hierarchy. It was already resisting, already occupying a state, already contributing to a balance that turned out to be one layer in a structure, extending all the way down to the erasure of structure itself.